What's up, Earth Science peeps? We're going to do the greenhouse effect today. So we're going to use those that diagram sheet, heating the atmosphere that we've been working on for a while. This is the last diagram on that sheet. It's on the back, on the bottom. We've already done insulation on the back. Now we're going to go one step further and do the greenhouse effect. Diagram itself looks something like this. Okay. You got yourself top of the atmosphere right here. I failed to write that down. Top of atmo. That's my lazy way of saying atmosphere. Okay. Let me focus that a little bit better. There we go. And then on the bottom there, we got Earth's surface. All right. And then roughly, 100 million miles away, we got this sun of ours. It's yellow, which is before in previous videos you might have seen. Orange is going to play the role of yellow here today. This is the sun. All right, S-U-N, not S-O-N. That'd be weird. All right, so we're going to look at what happens to the visible light that enters our atmosphere. Now, before we talked about how 50% of the light from the sun makes it into our atmosphere. I lost that diagram apparently, but I was going to show it to you again. But so 50% of insulation makes it through our entire atmosphere and it hits the Earth's surface and gets absorbed by Earth's surface. And then I think I said the phrase, and you might remember this: the sun heats the Earth and the Earth heats the air. Okay, well, that's basically the greenhouse effect. Okay, the sun heats the Earth. And the Earth heats the air. Okay, sun heats the Earth heats the air. Now I put quotation marks around the first heats because the sun is transferring energy through visible light. It hits the Earth's surface, and the Earth's surface collects it, absorbs the visible light. And when something absorbs energy, the energy is transferred to the substance. That's the difference between an absorber and an emitter. An absorber transfers the energy in, an emitter releases the energy. Okay. So there you go with that one. And then what we're going to do here is I'm going to show you I'm going to try to give you a visual of what the super hot sun light is like. Now, the sun, 6,000 degrees on the surface, 10,000 degrees Fahrenheit, right? It's wicked hot. So the energy it gives off is super high energy. And I'm going to represent that with these perfect waves. All right. Remember, one wave is it has to have a peak and a trough at the same time. And what I'm attempting to do here for you is I'm attempting to show you that these are really small wavelengths, right? This is insolation. Insolation, incoming solar radiation. And what I want to remind you is that insolation is visible light. Visible light is transparent to our atmosphere. All right. Transparent. That means it can go right through it. So check this out. I'm going to show you this real quick. This is a FET simulation. I love these things. What you're looking at is a flashlight on the left there, and it is spitting out photons of visible light. And if you guys remember, 99% of our atmosphere is nitrogen and oxygen. Look at what happens to the visible light with nitrogen and oxygen. It goes right through it, right? Goes right through it. Watch this. Visible light has no problem going through greenhouse gases. Carbon dioxide, water. Okay. Those are the two biggest greenhouse gases. So visible light virtually can go through our atmosphere unimpeded, meaning it can go right through it, no problem. All right, so it goes through the atmosphere, it hits Earth's surface. Earth transfers the energy to the surface, right? Here's another phrase I would like you to know. Good absorbers are good emitters. If something absorbs energy, it has to re-emit it. Otherwise, it's just going to get hotter and hotter and hotter and hotter and hotter, and then, it's going to blow up. So if something absorbs energy, it has to give off energy too. All right, so I'm going to write that down back on this beautiful diagram. We're going to come back to this. I'm going to get nitrogen back up there. So I'm going to write down, right, gets hot. So Earth absorbs, right? Remember, when it absorbs, the energy is transferred to the substance. So now we're basically taking energy from the sun and we're transferring it to the surface of the Earth. You feel that if you've ever walked on a blacktop or sand without shoes on a hot sunny day, right? It melts the bottom of your feet. So that's where that energy comes from. So the sun heats the Earth. It's using the visible light to transfer the energy to the Earth. The Earth absorbs and absorbs and absorbs. And as I said before, good absorbers are good emitters, which basically means Earth is going to give off light too. But the light it gives off is different, right? It has a bigger, longer wavelength, right? And it doesn't make it through the atmosphere totally. Okay, so Earth absorbs, and then I'm going to say Earth emits, right? Good absorbers are good emitters. Some basic physics here, folks. All right, good absorbers, good emitters. So I drew Earth's light in red because Earth's light, what we call terrestrial radiation, isn't red, but we often think of it as red because it's heat. It's infrared. It's infrared radiation. The problem with infrared, unlike visible, is it's not transparent. Something gets in the way. Number one greenhouse gas, most of us assume it's carbon dioxide, but it's actually, number one greenhouse gas actually is water. It's the number one. Okay. Number two is CO2. Then you got methane. Okay. Those are your greenhouse gases. Those are your greenhouse gases. All right. So here's what happens to the infrared. Infrared, going back to that one animation there. Infrared now. So we're going to shoot infrared. Infrared, you'll see it goes through nitrogen, no problem. Remember, 99% of our atmosphere, nitrogen and oxygen. They literally have nothing to do with weather and climate. Visible light can go through, and infrared light can go through, no problem. All right, but here's where infrared has a problem. Carbon dioxide. All right, carbon dioxide absorbs it. Now, does it absorb every single one? No, right? It absorbs it and then spits it back out. But it doesn't spit it back out in the direction it was going. It spits it back out towards Earth. It spits it back out horizontal to Earth. It slows down the infrared from escaping into space. Now, imagine putting more and more and more of those carbon dioxide molecules into the atmosphere. What's going to happen? More and more of those infrared are going to get trapped. They're going to spend longer in our atmosphere. And the more time that heat's in our atmosphere, warmer it is. All right. So that's really the greenhouse effect in a nutshell, right? Going back to this image that you might remember from the video clip we watched before we left. This is that astronomer, and she is holding a piece of glass up to her face, right? Why is she doing that? she's showing you that glass does not allow infrared to go through it very easily. It gets blocked. So it gets trapped, right? The sun can go through, the visible light from the sun can go through glass, but the heat that the earth gives off can't get through that glass. So the sun heats the earth heats the air. The glass is just like our atmosphere. And if you've ever sat in a hot car on a hot sunny summer day, you come out from like a movie, 2 hours in the sun, right? The car's just sitting there roasting, right? It might be 90 degrees outside. You go inside that car and it's like 120, right? Because the energy is getting in through the form of visible light. The energy gets transferred to the seat. It gets transferred to the seatbelt, to the steering wheel, to the whatever. When energy gets transferred, good absorbers are good emitters. So your seatbelt is giving off energy, but it doesn't give off the same energy the sun gives off. It gives off infrared, and infrared cannot go through the glass. So as a result, it gets super hot, right? So that's it. The sun heats the earth heats the air. Infrared can't get through our atmosphere. It has a longer wavelength, and these particular molecules absorb that particular type of light fairly well. Bada boom, bada bing. I got to get out of here, and I don't know how. All right, here we go. All right, folks. It's been a pleasure. See you next time.